Alright, today we are going to be looking at problem number 14 from problem set 1 for the forces. And I've pre-drawn the picture because I want to try to get through this in 10 minutes or less. In the first part of this problem, we have a person who jumps from the roof. And we need to focus in on this jumping from the roof, because what they really mean to say is that he steps off of the roof and then falls to the ground. If he was actually jumping, you would expect some sort of an upward velocity. That's not going to be the case. If that was the case, we would need that number. Otherwise, we wouldn't be able to solve the rest of the problem. So we assume that the initial velocity here in stage A is equal to 0 meters per second. So I'll just add that in there, 0 meters per second. But we do know that the person's going to drop 4.4 meters. And one of the things I want to bring your attention to is his feet are located here, and his feet at the start of stage B are located exactly at the ground. And what we really want to focus on is that every part of this person is dropping 4.4 meters from stage A to stage B. What happens in stage B is that the feet touch the ground, and so this person is not in free fall. That does not mean that gravity is not acting on the person. It simply means that the person is no longer in free fall because there are other forces acting on the person. From stage B to stage C, you can see the effects of the ground acting on the person. The ground doesn't allow the person to continue to fall, even though gravity is trying to pull them down, and the person wants to continue to move downward because of inertia. So there has to be this force upwards. Well, the force starts at the feet. So the rest of the body continues downward for a while, and we get that the torso goes down by 0.7 meters, which is not a small distance. That's a couple of feet. Now what we need to do in order to solve this a little bit more readily is to do some force diagrams. So I'm just going to put a little divider in here, and we'll examine our force diagrams. For stage A and stage B, our force diagram is pretty simple. Here's our person. Here's the force of gravity acting on the person. We don't have any other forces that are going on. For stage C, remember we're focusing on the torso. So we have a force of gravity downwards, and we have a large force from the legs upwards. I know that it's going to be a large force because we have to stop the person, and while we're trying to stop the person, we still have to counterbalance gravity. So it has to be at least as big as gravity, and then more, because we're trying to stop the person. So the next thing that I should do is list some givens. So I'm going to do stage A to B. Okay, so my givens for stage A to B, and I'm just going to stick with blue. I have my initial height as 4.4 meters. I have my final height as 0 meters. The initial velocity is 0. The final velocity, so I'll say the velocity at point B, is equal to, we don't know. The acceleration is negative 9.8 meters per second squared. And the time, we don't know. If we look at stage B to C, I'm starting off at, I'm just going to add in a little YB here. I start off at YB, which is 0, and we go down to negative 0.7 meters. The next thing that I need to look at is that I'm not sure what this velocity is, but I do know that the final velocity, the absolute final velocity, is going to be 0 meters per second. That's when the person comes to stop. Okay? I do not know what the acceleration is. It's not 0 because the person is changing in speed. It's not negative 9.8 because that would mean that the person would continue to accelerate downwards through the ground. I know that it's going to have to be positive, so I'm just going to make a little note over here. It has to be positive because we have a negative velocity coming down, and we know that we have to stop that negative velocity, so I'm just going to draw over here. This is the velocity at B. It's a little unclear there, but that's the velocity at B. And then the last bit is the time for stage BC. Now the nice thing is that we really don't care too much about our times. AB. We're interested in, primarily here, what is the force that's exerted on him. What is this? This force right here. Now to get this force, I need a couple of things. I need to know what is the mass, which is 42 kilograms, and I need to know what is the acceleration. So these are my points of interest. If I can get this, and I can get this, then I can solve for this, the force that the legs are exerting on the torso. I already know the mass. That's easy. They give it to me. That means I need to find out what the acceleration is. Now you can see that I have two other unknowns. I need one of them in order to solve. I can either use the no v equation and use the time to get the acceleration, or I can use the no t equation and use the velocity that he has right here at the end of stage B to get my acceleration. I'm not going to be able to get this. This is not what I'm going to be able to find. I am going to be able to find this one, however, the velocity at the end of stage B. And the reason that I feel confident of that is that I have that exact same given in stage A to B. It's my final velocity in stage B is going to act as the initial velocity for stage B to C. And you can see here that I can just use the no t equation to solve for that final velocity. So at this point the problem isn't that challenging. It's not so difficult. And I should be able to go through and get an answer pretty quickly. So I'm going to start off. I'll call this step 1 of solving the problem. I'm just going to say v squared equals v naught squared plus 2 acceleration from stage B times delta y. This is 0. The initial velocity was 0. So now, to solve for VB, I just take the square root, and I have 2 acceleration from stage, well, AB, I guess I should say. I'm actually going to just write it a little bit more precisely here. Negative 2g times y minus y naught, which is really just going to be the opposite of y naught. And that gives me a nice 2g y naught. So I don't have to worry about things like I don't have to worry too much about the negative signs because they're going to cancel out here. Okay? So the next step then is to figure out what the acceleration is for this phase. So to get the acceleration, I'm just going to use the same equation again, except it's going to be velocity final squared equals the velocity at B squared plus 2a delta y, where a is the thing that I'm looking for now. This, very conveniently, is equal to 0. So now what's going to happen is I'm going to be able to plug in, so I have 0 equals, and actually I don't even need a square root there, because I'm going to be squaring a square root, so I get 2g y initial plus 2a times y. And so now when I'm solving for this, I can just get rid of these 2's, and solve for A. So I have the opposite of G. Alright, my recording cut out at about 10 minutes. So in case something got cut off, what I'm doing right now is just plugging in this for VB when I'm solving for stage B to C. We're looking at the person eventually stopping, having been moving downward at this velocity VB. And in order to stop, the person's going to have an upwards acceleration on the torso. And so I can cancel out the 2's because there's 2's in each of the terms. And I now have the opposite of gy, because I move it over to the side, divided by y. And that's going to be equal to the acceleration. And you may be wondering, well, I had said my acceleration needs to be positive. How's that going to work out? I have a negative sign here. And the answer is that my y is also negative. So my signs are going to work out just fine. So I have negative 9.8 times y naught, which was 4.4. All of that divided by y, which is negative 0.7. And that gives me a final answer for the acceleration of 9.8 times 4.4 divided by 0.7, 61.6 meters per second per second. And that's actually a very large acceleration. It's about 6 times the acceleration due to gravity. And I'm just going to pop up here very quickly for the last part. Okay, my last part, my third part, I'm going to do a sum of forces equals m times a. And this is actually the easiest part. I have 2 forces acting on the guy. I have the force of gravity. I have the force from the legs. And that's equal to m times a. I know m, it's 42. I know a, it's 61.6. And the force of gravity is just minus mg. So I have minus mg here, plus the force of the legs, equals m times a. And we solve for the force of the legs, move mg over to the other side, and I now have m times a plus g. And if I plug in and solve, I get 61.6 plus 9.8 times 42, and we come out with 2,999 approximately newtons. So there's my answer. Just to give you a rundown of how this works. So I drew the pictures, and this is actually a very important part. I recognize that initially the person's going to be falling in free fall. And there's going to be a point where the person just touches the ground. After that point, the person basically compresses, kind of like a spring. And the compression is 0.7 meters for the torso, at least. The legs probably don't shrink down quite so much. In order to know how to solve this problem, one of the things I did was I drew my force diagrams and saw that I just have a free fall for the first part, and then I have the legs pushing up greater than the force of gravity, because otherwise the person wouldn't stop. Looking at this, I knew I wanted this force, and to get a force, I need an m times an a. Okay, and that's pretty straightforward, pretty standard. If you want a force, you need mass times acceleration. You also need the other forces that may be involved. In this case, that's just gravity. That's easy. We had that right off the bat. Check. This, the mass we had right off the bat. So the only thing left for us to find was what was that acceleration. So if we look at that particular stage with that acceleration, I just listed all my givens, and I saw that I needed either time or the velocity with which the person was falling. And that's easy enough to find. The time that it takes the person to come to rest isn't so straightforward. But the velocity with which the person is moving, we can find by looking at this, just the simple free fall stage. We know the distances involved, we know the initial velocity, we know the acceleration, so then we can get how fast is the person moving when they touch the ground. Knowing how fast the person's moving when they touch the ground, we're then going to be able to figure out, well, we've only got this distance to slow down. That person's going however fast, that tells us what the acceleration needs to be to bring the person to rest. And then the rest of it is just setting up the equations. We use the same equation each time, we plug in as appropriate, and we get our answer.